So in chapter 16, we're ready to start thinking about integrals, and we'll start by thinking not about antiderivatives, but about definite integrals. So that's exactly the way we started thinking about integrals in Calc 1, and so remember what a definite integral. A definite integral is, by definition, an area under a curve. And the way to think about it is to draw these very thin rectangles whose heights are determined by the function that you're interested in, excuse me, and then the area between two x values and under the curve is the definite integral. So this particular definite integral below is the integral from 1 to 2 of this function f of t dt. And remember, this is equal to an area. You want to think about this as area. In Calc 3, we're simply going to extend this idea to functions of two variables. So instead of a curve with a function of one variable, we get a surface with a function of two variables. So you can imagine some surface that's over the top of these rectangular bars. So now the definite integral, it's not an area, but now it's a volume. And I think of this volume as being filled with many, many rectangular bars, and the areas of the bases get smaller and smaller and smaller, and as I do that, I get more and more rectangular bars, and in the limit, as the area of the regions in the bottom goes to 0, I get the actual volume, excuse me, did I say area a couple times? Volume under the surface, and that's the definite integral. So again, this integral, this definite integral, or in this case a double integral, you want to think about this as a volume. So let me point out a little bit about this notation. So there's an r here. You want to think about this r as the region in the xy plane over which the surface lies that you're interested in. dA, that's there instead of a dx, so dA represents one of these small areas, of which there are many, lying in the xy plane. If you're interested in looking at the formal summation definition with the limit, that definition can be found on page 827 in your book. For right now, we're not going to worry about that too much. Here we'll content ourselves to consider a few examples. So here's the first example. We want to find the volume given by the definite integral over the region R, where R is the rectangle where x goes from 0 to 6 and y goes from 0 to 8. So that's this big rectangle in the xy plane. And there's a surface in the z direction. So if you imagine the z-axis coming out of the screen, there's a surface above it, below which is a volume that I'm trying to find. Okay, so we're not going to worry about being too precise. Obviously, this is just an estimate. Here's my strategy. I'm going to break up the overall region R into 4 subregions. So region 1, region 2, region 3, region 4. And above each of these will be a rectangular bar. So my picture is going to get too messy if I draw too many of those. But above each of those rectangles is a bar. So for example, the one I've drawn is the one that's between x equals 3 and x equals 6 up here, and then between y equals 4 and y equals 8. Okay. So the bar is above these values. Okay, so I'm gonna make a very, very rough estimate. So the definite integral over this region of f dA, I'm going to estimate by the volume of 4 bars, one over each of these regions. So since I started with this one up here on the upper right hand corner, I'll go ahead and finish that one. I'm just going to do something very rough. I'm going to look at the 4 values that are the heights of the 4 corners of this bar, and I'm going to pick something roughly in the middle, but I'm not going to worry about it too much. I'm going to throw out 55, I'm going to throw out 79, and I'm going to pick something between 61 and 68. let's say 65. So the first volume that I'm going to consider is going to be given by a rectangular bar whose height is 65, and the area on the bottom, well, the area on the bottom is simply this width times that height, so that's 3 times 4 is 12. So the height of the first rectangular, the area of the base of the first rectangular bar is 12. And overall, this gives the volume of that first bar. Okay, so now I'm just going to repeat that process for the other 4 bases in the xy plane. Okay, so let's go down to base, this one down here. So that goes from x equals 3 to x equals 6, and y equals 0 to y equals 4. I'm going to pick a value that's somewhere in the middle. I'm going to pick a height of 80. 80 is between the two middle numbers. Now the area of the base is exactly the same as the first rectangular bar. Its area is 12. Plus, let's move over to this first one in the between x equals 0 and x equals 3, and y equals 0 and y equals 4. And again, I'll pick some value that's in between the middle values. I'm just going to go with 87. So let's say the height of that bar is 87. The area of the base in the xy plane is again still 12. And then finally, we're going to go to that rectangular bar. Here's its base. And it looks like, let's pick a number in the middle, like so somewhere between 65 and 80. How about 68? That looks like it's roughly in the middle. So plus 68 times the area of the base, which is still 12. And I don't think I'm going to calculate all this out, but you can simplify your calculation a little bit if you factor out the 12 and write this as 12 times 65 plus 80 plus 87 plus 68. Okay, if you calculate all of that, then you get an estimate for the volume under the surface given by F and over the region from x equals 0 to x equals 6, y equals 0 to y equals 8.